Hi everyone. In this lesson we are going to talk about shear stress. In the previous lessons we talked about bending stress. Bending stress is the stress that is due to moment, internal moment, and the stress is normal to the cross section of the beam. Shear stress is transverse, is parallel to the cross section. Let's look at this beam here. I hold it, I applied supports like this on this beam, and I applied a force at the mid. What happened is this, you see the fracture, the fail of the beam. This is how the beam failed when I applied the boundary conditions like this. For static determinacy, I plot the supports like this, but what I did was just hold the beam like this and apply a force. So the force here, and my fingers hold the beam like this. Okay. When I increased the load, a fracture occurred, and the beam is turned into two pieces. So why did it not happen? Why did the beam not fracture like this? It could fracture. It should fracture in this shape. If the stresses that happened in the cross section was purely bending stress, the fracture surface is supposed to be like this, just flat. Because you remember in bending stress, the bending stress profile was like this. The stresses are maximum at the outside of the beam, so towards the outside it is getting larger and larger. At the mid, the bending stress, the one normal to the surface, is 0 at the centroid. But here it is not flat. It didn't break flat. It broke like this. So it has some horizontal component. The fracture has got some horizontal component. And if you look carefully, this horizontal component of the fracture is around at the mids. You see, if I plot it here, the fracture surface, so it is like this. So at the outside, towards the outside, it is almost normal. So here is the outside. It's almost vertical, but at the mids there is a horizontal component, and this is, guess what? This is due to shear stress. Okay. Shear stress and normal stress both causes the failure of the material. That is under loading. It is under loading like a beam. Okay, if you look at, by the way, this is a polystyrene foam, and it is a homogeneous, almost isotropic material. That means the mechanical properties are almost same on all three axes, x, y, z axis, the mechanical behaviors, the Young's modulus, yield stress, etc. They are same on all three axes. Okay, if we change the material and look at this tree branch, and it is a tree branch anyway. Okay, it's made of wood. I applied the same loading conditions for this. I hold it like this, and pushed at the midst. What happened is completely different to this fracture. You see that? So the horizontal component here is much more predominant. You see, the most of the fracture is caused by the horizontal deformation. So this is due to shear stress. So you may apply the same loading, same forces, and you may have the same magnitude of stresses, but the failure can be different, and this is due to the material behavior, material properties of the material, of the structure. So the shear stress becomes more important for the materials like this. It is important for all structures, but when it comes to materials, orthotropic materials, at one axis the shear stress will be higher than the other axis. So why is the shear is higher? Why did this material fail at the midst? It is because the shear stress is maximum at the midst of the section. It is opposite to what bending stress has. Bending stress is 0 at the neutral axis, but the shear stress is maximum at the neutral axis. If we draw the shear stress profile, it is something like this. It is 0 at the very end of the ends of the section, and it becomes maximum at the centroid or the neutral axis. So this is transverse shear, and this is the profile of the shear. It is not like this. This is shown in order to show the magnitude of the shear stress. So if I plot shear stress here, at the midst it is maximum. So if I move away from the neutral axis, it is getting smaller and smaller, and it becomes 0 at the tips. So if you plot a large cross section here, so at the centroid it is maximum. As we go away, it is getting smaller, eventually it becomes 0. Okay, this is transverse shear, and shear stress is a complementary stress. I mean, if you pick a stress element at any point, like this, if there is shear, transverse shear, there will be same magnitude of longitudinal shear. Therefore, the longitudinal shear is also maximum at the midst. Transverse shear is maximum at the midst. The same transverse shear is seen longitudinally. Therefore, this material, the wood, has failed at the midst. So the formula in order to calculate the shear stress is this: tau is equal to V times Q over I times T. V here is the shear load, the average shear load that applies to the section of interest. Q is the first moment of area. So where is this? If you want to look at the tau shear stress at this point, you plot a line, okay? Plot a line parallel to the neutral axis. If this is the neutral axis, you plot a line parallel to this neutral axis, and it pass through this point of interest, and you want to look at the shear stress at this point. So Q is the first moment of area above or below this point, above or below this line. You choose, let's choose the area above the line. So if you multiply the distance between the centroid of this area and the neutral axis, say this is y1 and this area a1, so y1 times a1 is the first moment of area. You will remember from the previous lesson, first moment of area looks like moment of a force. So this is moment of area, and the other one is moment of force. Okay, Q is the first moment of area. I is the area moment of inertia of the cross section. The I belongs to this cross section, and you remember that it is BH cubed over 12 plus A times D squared. T is the thickness of the line that you plot here. Okay, so I and V doesn't change for the section. T and Q changes within the section. It may change depending on the type of the section. So T is this, Q is y1 times a1. So if we choose another point like this, Q will increase because the area above this line will be larger and the distance will get smaller, but the area will become much larger. Therefore Q increases, T doesn't change, I doesn't change, V doesn't change. Therefore, as we approach to the centroid, tau will increase. So you may ask why the shear stress is maximum at the mids. Let's look at this. Look at this foam I made. I put some soft material at the mids of two pieces of foam, and when we apply a load like this, you see that the lines at the top getting shorter, the line at the bottom getting larger, it is elongated, and the line at the mid, it didn't change the length. So that means there is a compression at the top, there is a tension at the bottom, but there is also shear stress that is happening throughout the cross section. Okay, and if I take out a little piece from here, let's make a cut and take out this piece. Before doing this, let's plot shear moment diagram of this beam. Okay, what do? We first do free body diagram. There is force here. Since this is equal distances, these are equal distances, therefore there will be half of the F here, the reactions. So this is the free body diagram. Say this is L2 for the distances. Just below that we plot a shear diagram. So here the shear is F over 2. In the second discontinuity towards the until the second discontinuity, the shear doesn't change. It is F over 2. It's positive. At the second discontinuity, we go down by F, so it becomes minus F over 2. To the next discontinuity, it doesn't change, and at the third discontinuity here, it goes up by F over 2. Okay, it is positive. This one is negative shear. So just below that, we plot moment diagram. So here you see that there is no external moment, therefore the internal moment will be 0 at the beginning, at the origin of the beam. If we plot the discontinuities, so how will we go to the next point, next discontinuity? We look at the shear diagram. It is constant, therefore the moment will be a slope. It will increase in the form of a slope, and the magnitude of the moment is F over 2 times L over 2. So this one is F over 2 times L over 2. So the moment here, F times L over 4. So from here to here, again the area here is minus F over 2 L over 2. Therefore we will go down by the same amount, and the moment will be 0. So here you see that the maximum moment occurred at the mid of the beam. So if I choose a section near the mid, I take out this. So it's not easy anyway. I cut another one. Okay. I just took out a piece. You see here, I took out a piece. Right. So I want to show some forces and stresses on this, but it is very small. So if we enlarge it and put a bigger version of this, so this is zoomed in. This is the section we cut. Assume that this is the section we cut. And if we want to draw a free body diagram of this segment, this little segment, how will we show the loadings? The moment, just to the right, the moment is, so what is it? Is it positive or negative? Say that we cut out the segment here. Okay, segment here. So the moment to the right of this segment here, moment here, is larger than the moment here to the left of the segment, and they are positive. That means they are in this direction. So on the left face of this segment, the positive sign convention is this. This is when we look at the left face of the segment, this is the positive sign convention for the moment. For the right face, this is the positive sign convention for the moment. So the moment here, if the moment here is m, moment here is m plus dm. Does that make sense? It should make sense, because we plot the segment here. You see the moment here is larger than the moment here. So this side is larger. So if I go to the next page. Okay, let's plot the segment here. Okay. keep the segment here. So the moment, where is it? I draw it with this. This was m plus dm. This was just m. We know that moment causes bending stress, and how do we show it? With a bending stress profile. There is compression at the top. There is tension at the bottom. Okay. This is the bending stress caused by m plus dm. If we do the same, if you plot bending stress profile here as well, it will be something like this. Now the compression at the top, tension at the bottom, half. Do you notice the difference between these two profiles? You should notice that the profile here at the right face of the segment, the section, the right face of the section, the bending stress profile is larger than the one at the left. It is because you remember sigma equal to m times c over I. C and I are the same for the both faces, but m is different. This one has got more moment. Therefore, the bending stresses will be slightly larger on this face. If we want to write horizontal force equilibrium equation for this free body diagram, horizontal force equilibrium equation, you will see that the force, so for force we multiply sigma by the area. You see that the length of the arrows here are equal to those here, and the length of the arrows here are equal to those here, and they cancel out each other. Therefore, this segment is in static equilibrium upon this moment, internal moments. For the section, they become external. But you understand that these equal to those here, these equal to these. Therefore, there is a horizontal force equilibrium for the section. Okay, if I make a cut like this, or let's cut it, anyway, I cut first somewhere here to the top. Now my section, my part is smaller, and if we draw the shear normal stresses, if we plot the normal stresses, this is the condition, right? Now forces this direction, stresses this direction, and stress on the left. You think this structure can be in equilibrium if the stresses, if these were the only stresses, then this structure would not be in equilibrium, because the length of the stresses, the magnitude, you see, for each corresponding arrow, those on the right is larger. Therefore, this segment would move to the left upon these loadings, upon these stresses. but it doesn't happen. What happens is there is a shear stress just below this section. So this was the part that we dealt with. Okay, we made a cut, we take out a piece and plot the stresses, and if we write horizontal force equilibrium equation for this, we will see that for each arrow, for each line of arrows, those on the right is larger than those on the left. Therefore, if we had no other stresses, this little segment would move to the left, because those on the right is larger and they are pushing to the left. So we need something to keep this segment in equilibrium. It is the shear stress that will hold this in static equilibrium. So it has to be in opposite direction. Okay. And as we cut more, where did we cut it from? Anyway, so say that this is the original shape. We cut somewhere here. If we cut around here, so near to the neutral axis, so our segment would be larger, right? Now the segment is larger, and this imbalance, here it is not in balance, we needed shear stress to keep it in equilibrium. Here the difference is even larger, because there is more arrows here and it adapts. Therefore, the shear stress that is needed to keep the structure in equilibrium has gotten larger. So, as the segment is smaller, the shear stress is smaller. As the segment gets larger and larger, the shear stress just in between needs to be larger. Okay, that is the reason why this wood has failed at the mids. The shear longitudinal shear stress is largest at the mids. Okay. What else to say? I hope it is understood, and I will not derive the shear stress formula. You can look up the textbooks. I just try to explain you the logic behind the shear stress profile. I hope you understood it. And let's make an example. Okay, let's draw. What should we work on? Let's draw a simple beam here, simply supported beam. Say that there is a 100 Newton load and the section is what can we say? Say that this is 10 millimeters. This is the height is 40 millimeters. And I just make up the problem. And we can say that this is 200 millimeters 200 millimeters. What do? We draw the free body diagram. Since these are equal size, the reactions will be the half of the applied load. 50 Newton, 100 Newtons here. Okay, next, shear load diagram. Should be Newton. We go up by 50. Go to the next discontinuity, the same magnitude, and go down by 100. Go to the right as minus 50 and go up by positive 50. This is the shear diagram. Then moment diagram. Let's say this is Newton meters. This is 50 times 0.2, right? 50 times 0.2 meters. Therefore it is 10. We start from 0 because there is no external moment at the origin, and the increase is a slope. So what is it? We found it as 10, right? 10 Newton meters. And here it is minus 50 times 0.2, and we go down by minus 10, and it is again a slope. Okay, so the maximum moment is 10 Newton meters, and the maximum shear, you see that Vmax is 50 Newtons. Let's determine the maximum bending stress and maximum shear stress on the beam like this. I just enlarge this cross section so you can see it. 10 millimeters, 40 millimeters height. Okay. So for the maximum bending stress, M max times C max over I, 10 times, what is C max? So the neutral axis is at the mid of the rectangle. So the C max is 20 millimeters, that is 0.02. 0.02 meters, divided by I, which is B is 0.01, H is 0.04 cubed over 12. What about A times D squared? D is 0 because the distance between the neutral axis and the centroid of the shape of interest is 0. This is a very simple geometry, a straight rectangle. Therefore the centroid and the neutral axis of the section is at the same point, therefore D is 0, so this term is cancelled. Okay, let's calculate it. 0.2 times 12 divided by, let me calculate it using my calculator. The result is So I haven't written it here, but the result is sigma max equal to 375,000 Newton millimeter squared. Newton over millimeter squared. And what does it make? It means 375 kilopascal. 375 kilopascal. This is the maximum bending stress that we see on a beam under loading like this. Okay, we found bending stress. Let's proceed to the maximum shear, and let's plot the stress profile, normal stress profile. It is positive, therefore there is compression at the top, tension at the bottom. 375 kilopascal here, same here, the magnitudes are the same, and it is 0 at the neutral axis. This is the bending stress profile. What about the shear stress profile? Shear stress profile, tau equal to VQ over IT. We talked about Q in the previous lesson. Also we talked about the I, which is the area moment of inertia. You can find them in the previous lesson. So the Vmax, tau max, is equal to Vmax times Qmax divided by I times T. I and T are the same all across the section. So the section was like this, or just like this, and T is same all across the section. Also the I doesn't change, but the Q changes. Q is maximum at the centroid. So let's determine Q first. Q max is equal to so if you draw the cross section and we cut here, choose a point here, and the area just above the line. So the centroid of the area is 10 millimeters away from the neutral axis, because it is total, it was 40 millimeters. This area is 20 millimeters height, and its centroid is 10 millimeters away from the centroid, the neutral axis of the whole section. Okay, it's 10 millimeter, Y is 10 millimeter, and the area is 10 times 20. Therefore, Q max is equal to 2000 millimeter cubed. Okay. So we did it in millimeters, but we can convert it into meters, also pascals. Okay, T is equal to 10 millimeters. I is equal to h cubed over 12. B is 10. H is 40 cubed over 12. So the result I is equal to 53,333.34, sorry, 3 millimeter cube, millimeter to the 4. Sorry, this is the millimeter to the 4. This one millimeter cubed. This is millimeter to the power 4. Vmax, as we have found, it is 50 Newton. Therefore, the tau max 50. This is in Newton. times 2000, this is in millimeter cubed, 333 times thickness is 10. So here we have got millimeter, here we have got millimeter over to the power 4. So this and this goes away. What we get is Newton over millimeter squared. Let's calculate this. This goes away. 50 times 200. Okay. The result is, so max is equal to 0.1875 Newton over millimeter squared. So what is it? It is 0.1875 megapascals. If you convert it into kilopascals, it is so 187.5 kilopascal. So you see here the maximum normal stress is almost double the maximum shear stress. Therefore, for an isotropic material like this, where is a foam here? For an isotropic material like this, most of the fail is due to the bending stress, because it is maximum, as you see here, the maximum is the bending stress is larger than the shear stress, but where the bending stress is small, the shear stress, effects of the shear stress became visible. The bending stress gets smaller at the mids and shear stress gets larger at the same around the mids. Therefore we can see the effect of shear stress. But for a wood like this, you see that the shear failure occurred before the normal stress. You can also see the normal stress, the effects of normal stress. You see the fibers has separated at the outside of the section, but the most of the fail is due to the shear. Okay, this is the end of the lesson. I hope you understood, you enjoyed the lesson. Thank you for listening.